I think we are live. Hello, Ben. How are you? Hello, YouTube. How are you?
Hey, doing well. How are you, my friend?
Oh, we're in the middle of that storm that just swept across the country. We've got we're not even freezing rain. We're just rain where I'm at now, and it melted all our snow.
That's a drag.
Yeah, yeah. Oh, my turkey died this week. On a personal note,
that's a
he was 8
drag.
years old. Yeah. He went downhill fast, and we knew it was coming. He was old. So
winter gets the
it filters them out. Yeah, we lost a chicken too. Same thing. The chicken was like, I'm not going to make it this year, and just kind of shut down. It's kind of like an old electrolytic capacitor. It just dried out, and it started, the ripple current, the heating, and it just, aged quickly.
Yeah.
So somebody just told us we are live. Thank you.
Yes, I
very
see that
good.
now.
Always good to know.
I finally pulled up the YouTube. I'm going to open that. Oh, what does it say? Video unavailable with restricted mode enabled. What the hell? It's like the last person signed into this computer was one of my children.
Oh, wow. Oh, right. Well, but I'm unrestricted.
As me.
Yeah, I'm unrestricted, so I don't know why you can't see it. Other than the word YouTube is involved. Thank you, Dave. So you can't see the chat channel, is that what you're saying?
Yeah, I'm trying to get onto that, and I can't remember how to turn off restricted mode. Let me see. How do I do that? How do I... Settings?
Well, if you don't get it, I'll watch the chat channel for us.
Well, you'll be doing most of the talking today, so...
Yeah.
Let me do a quick search. Sorry. You start. I'm
not a problem. Well, so while you're doing that, one of the things I was going to spring on Ben this week before we talk NTSC was he was saying that he wouldn't mind adding a good audio analyzer to his bench, and the engineer in me started saying, well, couldn't we make one? And of course the answer is no, probably not, because making test equipment is an art, right? You have to make something good enough to test the stuff you're trying to test. But I swear to gosh, you can get pre-made modules from Analog Devices. It's already laid out, 24-bit Delta Sigma AD converters. They've already done the software, so you could model all this up with a few $100s worth of hardware. And then modern coding techniques sure get you a lot closer to being able to analyze audio, using regular library calls like in Python. So let's see, make sure your theater mode is turned off. Alan is saying.
It wasn't that. No, restricted mode was on this browser for some reason.
So you're good to go
computer.
now?
Yeah.
Okay.
It's all good
Very
now.
good.
I can see the chat. I can see us live. Yeah. So I was thinking about this too, because I started looking for an audio analyzer.
Right.
A few years ago, several years ago, actually, by now, probably even 10 years ago, because I was thinking, I'd heard of Audio Precision. They're like the industry flagship, Audio Precision, and they have software for a PC. It integrates and it does all your nice graphs, does THD versus frequency and power output for, like, it's the Audio Precision System 1 is the industry standard and flagship for testing power amplifier designs for THD, noise, power output, frequency response, all the damping factor, all the things you want. The problem is a System 1 or whatever the current version of it is going to set you back. Even used, they're like $10,000.
Right.
They're very expensive.
And the old HP stuff is still $1,000 when I looked on eBay.
Yes, and in dubious condition. They're so old. The HP 8903Bs or 8903As, I'm not quite sure what the difference is. I did know, but I've forgotten. I think the B is the better one. Yeah, you can buy one broken and it'll be $500 or $600 on eBay. They're outrageous. And the tough thing about it is the way that the Audio Precision one works, the way that the HP one works, and various others that I've looked at. They have an array of extremely low distortion, low noise sine wave oscillators that are
Right.
using FETs. They're oscillators
In
that
a
use
stair
FETs.
in a staircase. Yeah.
They're not DDS. They're pure analog
Right.
oscillator. They use FETs with light bulbs for
For the source of the RMS, conversion.
You put a light bulb in, I forget where it is. You can do it with op amps too nowadays, but you need a light bulb in the circuit because what you have to do. So here's the thing: in linear systems, like an amplifier with a feedback loop, you have gain and phase, and you have phase margin and gain margin, and you have poles and zeros. If you have, the moment you create feedback, you have a system with a transfer function that has poles and zeros. And to make a perfect sine wave oscillator, you need a pole exactly on the line between if you think about a Laplace transform, and if anyone hasn't studied linear systems, sorry if I'm losing you here. Stay with us. We'll get to more interesting stuff. But you need a pole. You need complex conjugate poles exactly on the line between the right half of the S plane. S plane is your complex frequency plane. That's kind of like we look at it as 2 dimensions, but it's really a 3-dimensional surface that is the response of the circuit. As frequency. Frequency is your J omega axis. That's your complex axis, and gain is your real axis. And if you put poles, if you design a circuit and you put poles in the right half of the plane, it becomes unstable and will oscillate. But if they're just past the line, the oscillation, because of the gain in the system, the oscillation will saturate and you get something more like a square wave.
Right.
If you want a perfect sine wave with no distortion, the poles have to be exactly on that line that divides stable from unstable. So it will oscillate, and it's hard to get the oscillator to start, and it's hard to get it to continue without distorting. And to do that, they use this trick with a little light bulb in the feedback circuit that if the element in the light bulb, the filament heats up, it increases the resistance. If it cools down, it decreases the resistance. And so it forms this perfect balance that keeps it exactly in the right spot. Then they have to filter out the, you take your, what looks like a pure sine wave, but it's still not perfect. You notch filter it.
Right. Get rid of all other energy,
you get everything except for your sine wave, which is all the distortion out of your oscillator. And then, so you have this divided signal path. You have your almost perfect sine wave, and you have all the residual components of it, which are distortion. And then you invert the distortion and add them back together, and that makes it even more pure. And then you feed that into your device under test.
Right.
And then you do the same thing on the other side. And so all the circuitry that does this with really low noise and doesn't introduce its own distortion is really, really hard to do. And that's why these HP 8903s are super expensive, even though they're 40 years old by now. And I really would like one. I'd really like an audio precision system one, but 10 grand, I'm not going to be able to do that. But I've seen on the forums, people have actually built their own. Some people have designed it and built their own, but it takes so much time and effort. I think it's...
And you need a standard. You have to know how well you're doing.
Right.
So you need a... Right. But the... So, and you and I were talking before, is it possible to use DDS to create the sine wave these days? And the answer is we don't know. Maybe not. Right?
I think that DACs are good enough today that you could get a pretty decent result, but you still need to have digitally controlled notch filters and all that other stuff to null out your fundamental, separate your fundamental from residual, and do all that fancy stuff. It's doable.
Right.
I think it's doable. I think audio codecs are pretty darn good now.
So the reason I mention all this is we have a Discord channel, and you can find the Discord invite at Coriolis-effect.com. Coriolis effect being, of course, which direction your toilet spins. Not really, but that's what people think of. And Ben being from south of the equator and me being from north of the equator, we have opposite we have opposite effects. But anyways, maybe this is something to discuss. If any of you math wonks and instrumentation people want to make an audio, or at least discuss it, what would be involved in an audio analyzer? It's probably just a week from now, I'll probably be, what? Audio analyzer? Why am I still talking about that? But I've been thinking about it for a couple days now, just what all would be involved. And, and you hit it on the head. Spectrum analyzers you can get, but you need a good, clean oscillator to determine the total harmonic distortion is the main use for it, right?
Yeah, that's right. Alan Wilkie just commented, the light bulb in the feedback path is to keep the oscillator amp linear. That's true. Yes.
Yeah.
He is so much better at, with his experience as an instrument specialist and helping to teach people how to use them over the years. I guess he can sum things up way more succinctly than me. Thanks, Alan. That's a great comment. And
very good.
Actually, this is a question for Alan on the chat. I don't know if you're paying attention. You can answer this whenever you get a chance. I'm curious with the RF test instruments, what kind of distortion levels are typical in oscillators for RF testing? Because I use low cost VNAs because I don't have a big tool budget and I don't work for a tool manufacturer. And I think, like the mini VNA Tiny is really handy for a radio ham like me on a tool budget, but I'm pretty sure it's just using some very basic DDS and probably only 8 bits or even lower resolution, maybe even square waves, heaven help us, for some of the signal generation. But talking about signal generation...
Yes, and notch filters. We're going to show a notch filter here in a second. As people may know, we showed a monitor last week or talked about monitors, and we got into... my background was I was a TV repairman. My electronics career wasn't based on math. It was based on my ability to repair stuff, plain and simple. And then I learned how to act like an engineer, and some of my stuff ended up acting like computers, that I was working on. But we had talked about the NTSC generator, the National Television Standards Committee, is derived the standard that we called TV sets in the old days. And then there's the other one, PAL, phase alternating line, which was very popular in Europe. And I just happen to have a couple of old test pattern generators. And so, these would still be useful for working on monitors. So that's why we're going to talk about them today, basically, here's some old cheap test equipment that can be useful to us, and also explain some theory here and even some history, because I have a convergence board shown here, which, trust me, these things here you do not want to have to mess with if you can help it. So what I've got is I've taken I'm not sure you can see my mouse. No, you're not going to be able to.
Oh, well, I saw you move the convergence.
The convergence board, right, but you can't see my mouse. Yeah. So down in the bottom right, I have an NTSC generator. And let's see if you could. So I've got my NTSC generator here. I've got a second smaller Tektronix one that's not plugged in.
Yep.
And then I've got a video amplifier here.
Yep. That's
and
like
so what I've done, right?
Yeah.
So I've split it off to a screen capture, which is the bar display we see. I've thrown one to the scope. I've thrown one to the Vectorscope, and I'm going to try and show that later today. And I forget where I sent the fourth one to, probably just a regular monitor or something. Oh, to the oscilloscope. So I threw on the oscilloscope. So let me stop and back up, even though the bars are pretty and stuff.
Yeah.
The act of aligning a picture tube starts with the static part, what we call purity. And I can use my analyzer to make purity. Or at least I could earlier.
And that makes that gives you okay, right.
So I can make white. I don't know if you can hear me as well from way back here.
We can hear you. Yep, you can do each color just as a block.
Right, and so we would start with red. We would start with the red gun and make red purity. Actually, it would come out kind of a pinkish color, is my memory. But if you can't make solid red completely across the screen, you're going to have a heck of a time making colors the way you want to. So we start with the purity adjustments of the screen, and those were those little magnets that are literally on the tube, the neck of the picture tube, where you're bending the beam in the center.
Yeah.
And so the idea is, go ahead.
If you didn't see, that was discussed in our call last week, where we were covering a couple of different monitors. We started out with a Amiga 1084, Commodore Amiga 1084S schematic, if I recall. But you discussed and talked about those physical adjustments with the magnets. Yep.
Right. So go to Coriolis-effect.com or the YouTube channel, and you'll see last week's where we talk about that. So, and now I'm going to show you these solid colors when I show you the Vectorscope, because it helps understand the Vectorscope, which is a different piece of equipment. So the very first thing we do is our purity test, and then after that, and purity test is our ability to use the red gun in the picture tube to hit all of the red dots on the phosphor target. And then what happens is an electron gets accelerated through the picture tube, hits phosphor, and the phosphor emits. There's 3 colors of phosphor with different chemistries that make different color lights when they're excited. And so first we test our ability to shoot all red, and then we do our blue and our green after that. But that's the purity test. After that, we used to start with 3 dots in the middle. This one doesn't have it, but we check our convergence in the center. And when you initially try this, what you want is a white dot. And when you start, you get a blue dot to the up and a green dot kind of down and to the right. And this is in the center. See, here we got dots throughout this target, but generally we're looking at just the center ones first. And what we're doing is we're adjusting the ability of the gun to shoot straight. It's like zeroing in a gun, a regular weapon, right? And then we go to, well, can we do on the edges? And it gets trickier because, as we talked about, we're scanning the phosphor from top to bottom, and we're using a magnetic coil, and it's not linear. And we end up with these things pin-cushioned in or keystoned. A TV picture looks horrible without all kinds of adjustments that we've learned to make over the years, right? Yep. Now, so here's the next pattern I would do as a TV repairman. I put this pattern up all the time.
Oh, yeah, the grid.
My grid, right. Now, the convergence is, in theory, perfect on this because I'm going into a frame grabber. But on a monitor, what you would typically see is on the very edges, you'd see blue was always the worst to hang out for, just the way the gun's manufactured, it seems like. And you ended up with a board. Let me try and show it here. I gotta get let me make it bigger. So this is a typical convergence board where there's a control for everything. So you start by adjusting the red and blue horizontal, then you adjust the green horizontal, then you adjust the red and blue vertical, and then you adjust it for pin cushion. And if you look down the right side, you'll actually see it says key, pin. These are all these adjustments that you had to make to slowly bend that crosshatch pattern to where it would be a white crosshatch. And honestly, on old sets, we never got it perfect. On the edges, you look at old TV set, you'll a lot of times see blue on the edges.
What's this board from? Things. I'm curious. Do you know what?
I just grabbed it off the internet. Okay. This is from a projection TV, so it's not even that old, but it's not that new either.
I was gonna say it's a typical
nowadays we don't need these
single-sided board with jumper wires everywhere.
Right. Alan just said he hated Convergence in the old days. And, I loved it because that was kind of, that I was trained to do it. So I was like, okay, here's the thing I can do that the home user can't do that has a great effect right off the bat. So now TVs got so they didn't need these, but cameras used to use these things, these convergence boards, for the same reason. A camera used to scan a target, and it needed to be converged. And a friend of mine named Kerry Sagety worked for RCA in the broadcast camera. And Ben and I were talking about the old broadcast cameras, how big they were. And they were based on Plumicon tubes and Nuvicon tubes. They're basically like a picture tube, in a camera. And they had the same problem. We had to converge the picture tube. Well, what Kerry's group did for RCA was they would joggle. They learned to do it in a microprocessor. So imagine a time in history when we say, hey, let's put a microprocessor in a camera and make it converge itself. And it's like, well, there was no flash memory around then. So you know how this camera stored the results? EEPROM. It was its own EEPROM burner.
Wow.
And that was kind of, that I'd seen several things in the old days that burned their own EEPROMs.
Well, I guess that would work fine, because even though the EEPROMs of yesteryear didn't last and didn't have that great a reprogrammable lifespan, but someone would probably only do the convergence once in a blue moon, so it was probably no problem.
Now in TV sets, you had to do it when you moved the set. Especially projection TVs had a whole procedure. If you move the set, guess what interferes with the TV? The magnetic lines of the Earth, right?
Oh, yeah.
they can.
Everything.
A projection TV could be, the older ones could be that sensitive that you would you'd move the set and you'd have to run. But then they came up with the self-convergence, and you would sit there and watch your set flash red, green, and then a dot would jiggle in the green and do all the convergence.
Yeah. Well, back when I was doing lighting, back in the 90s, I was doing lighting and pyrotechnics, and worked on a lot of different corporate gigs. And the corporate gigs, they would always have the gigantic projectors, CRT gun projectors, and then later they went to LCD projectors. Man, I don't know how you get the heat out of the LCD in those things. That's a lot of heat. But they'd have the 3 gun projectors, and the AV guys, every gig, they were going through this exact process, and the projectors were good enough back in the 90s. They had it all done under microprocessor control as well. So same kind of deal. Right.
So here we are back at the color bars. So then you put this up, and what you're expecting to see is exactly what you see here. It's like, can we make white? Can we make red? Can we make blue? And there's you've seen various versions of this. This is a test pattern like they use on TVs for a purpose. This is like, and there was a time when TV stations stopped transmitting at midnight.
They just put a test pattern out all the wee hours of the morning. That's right. The last show ends, you get a 1 kilohertz tone or a 440 hertz tone.
Right.
If you want to tune to it. I forget what it was. I think it was probably a lower it was lower than 1K. It was probably 440
Probably
hertz.
440, yeah.
A concert pitch, and
concert A,
with color bars surrounding it, and this pattern thing in the middle. It had circles and different meshes and lines coming out of it for measuring. It's like, okay, so they send their techs out at midnight. I get it.
So, and I had a radio, I hung around a radio station when I was young, and so I knew broadcast engineers, which they knew radio, but they also knew TV. And one of the things they taught me was that a TV station puts out the most power when it's making a black signal, because of the way it's transmitted. It's the most amplitude. So we're used to black being a low voltage, but in transmission it's the high.
Why would that be? Is that because it's like equivalent of continuous wave?
It's almost up to the sync pulses. Yeah, right.
Interesting.
So
Yeah, I never thought about that.
Looking at the oscilloscope we see here, we talked last week about the vertical and horizontal retrace. These are blank lines, and then this here is the very first line on the TV, on the scan. And we see the very first color that you can see right here is the northmost. It's the highest. Well, in this, black is down, white is up. At this point in composite video. So here's our white bar right here, and you can see the brightness. It's as bright as anything. Then our yellow bar is as bright, and we go down the staircase, and this is sometimes it's called color bars, sometimes it's called staircase. I'll show a different staircase.
Can you
and then
zoom
blue
in?
being the dimmest.
Can you zoom into
yeah.
just one color and show us exactly what the
Let's
color
try
itself looks like?
So, and I'm used to this on analog scope, so I'm not sure what it'll look like.
It's just a sine wave.
Yeah.
And does each peak on that wave correspond to a pixel? Or no, it's analog. There are no pixels really, but because we just talk about lines of resolution, which is horizontal lines, and there's 270. Right. But if we were to count the number of essentially sine wave pulses in the yellow bar,
right? Do we get 480 of them or whatever? And that's a great question.
Well, we would get as many as the width of the bar on the screen.
Yeah. Yeah.
Right? I'm probably wrong, right? Because I think.
Oh, here's another display.
That's your spectrum.
Spectrum analyzer on it, and that notch right here. Now it's jumping around because this is it's capturing during the visible part of the display and also the invisible part. Look at this notch. That is where we cut out the 3.58 megahertz color subcarrier.
Right.
The carrier, I mean. That's a subcarrier.
Right. That's done with the comb filter.
That's done with the comb filter. That's right. So look at that. I loved it when I saw this setting up for the show and I saw that notch. I did not expect to see that notch. And so here's our color information that you were just asking about, those sine waves. And to prove it, I'm going to put this in black and white mode. And now we just have the noise, the video noise in the spectrum analyzer. So here's what the display looks like now. Now, here's another test we used to do, and we still do it to this day, and that's called Grayscale Tracking, right? It may look to you like, based on your monitor at home, when you look at this, these should all be shades of gray, not turn pink or green or anything as we go through. But if you see like pinks, like in this column, it's a little pinkish on one of my monitors and not on another, which just goes to show it's all about, every step of the way, including the thing that your eyes are looking at, is part of that color purity, or in this case, grayscale tracking. So we would throw it on a black and white screen then and make sure that grayscale looked good in grayscale.
Alan's giving me the download on the color encoding. It is pure analog, because he's saying, yes, we have the 3.58 megahertz subcarrier that you mentioned, but then in the different colors, as the line traces across the screen at that location, it's the amplitude is saturation, he's saying, and the phase of that sine wave is adjusted to change hue.
It's the color, right?
Yeah.
Right. So
it's bloody complex and very clever. The people who invented these composite video signal systems have to be amongst the best engineers ever, in my opinion, because this is just to do all of this back when it was purely analog. And that makes sense why we have a vectorscope. Of course, that makes perfect sense. There's your vectorscope, because we're dealing with phase angles. So the phase around the scope is your color, the phase angle, and the distance of the dot or the line on your Vectorscope away from the origin is going to be your saturation.
Right. So brightness is how much amplitude there is, and then the color is encoded on a subcarrier. When we decode it, we get a shifting phase, and we can only shift the phase 3.58 million times a second for the information to be intelligible. And that's what sets the maximum number of color dots on an old TV set at whatever, now I've forgotten, 320. Like on the Commodore 64, we can't do 340. There's not enough not enough cycles of the 3.58 in there. You need an entire cycle to get an entire color pixel. But what they did in the Amiga was they said, hey, the bandwidth of the color is 3.58 megahertz. You'll notice I do this whenever I talk about color because I picture phase angles, right? But but we can change the luminance up to about 4.5 megahertz, where the audio subcarrier is. So what they did was they did something called hold and modify, where they go to do a pixel and they pick a color, and then they pick a brightness, and then halfway through the pixel, they pick a different brightness. Well, it turns out we can do that. The luminance has that value, and we left the color the same. And then on the next pixel, we pick a new color, and then an initial brightness, and then a second brightness. It was called hold and modify. So we would hold this phase angle, we would hold
That's like dithering.
This amplitude. Yeah, and then we would come up with the second amplitude for it. So you could make red into pink, for example.
Yeah, and Alan's saying...
Or a different shade of red.
Part of the reason for the complexity, of course, is backwards compatibility with black and white.
I was going to talk about that. Thank you. So the beauty of it is, the original RS-170 monochrome started out as true 60 hertz, and I can't do this math, but nowadays the horizontal is 59.94 megahertz, and the difference is, well, had to go somewhere. Putting a 3.58 megahertz subcarrier in there had to have some effect on the math, and so the horizontal frequency effectively changes. Yeah, never twice the same color. Alan's mentioning. Alan, by the way, we're talking to on the channel is a Tektronix RF field applications engineer, knows way more about this stuff than I do.
And he has a great channel as well where he's if you're all not subscribed, you should, because he's got some amazing educational content there on how to really get the most out of your instruments.
All right.
I was going to say, he mentioned the NTSC, never twice the same color. We also had one in Australia for, and this is a completely different thing, but just since we're talking about funny alternative acronyms, that was NTSC. For telecommunications, the guy that was kind of my mentor in electronics when I was a teenager, Richard Freeman, I've mentioned him before on the show, he's a wonderful friend. I need to get in touch with him again, actually. He was a tech for a long time for Australia's largest telecommunications organization. And I asked him one day, what does ISDN stand for? I was a teenager at the time. He's like, I still don't know.
Isosynchronous Digital Network. I used to know.
Integrated Services Digital Network.
Digital Network. Right.
Yeah,
I met one of the engineers that worked on it at IBM. Yeah.
His immediate answer is, I still don't know.
Yeah. Well, I was an ISP for years, and we used to do these nailed-up ISDN lines. Yeah. We used to do these 128K lines and bond them together to make 256, and I was doing it with ISDN lines, and this is like the late 90s that we used to do that. Oh, yeah.
Like, that was
we're going always on. Oh, yeah, 256K. I could go up to 512K.
Yeah, we can run 4 telephone conversations, and our computers will drop out while there's 4 lines, 4 phone calls going on, but whatever.
Okay, so I'm going to show the Vectorscope. Hopefully you can hear me.
Yep.
There are these boxes drawn on here where certain colors by spec are supposed to be. And there's a box, and I missed it, actually. Here's the box, but here's red, okay? So what that's showing is when I make red, there's the phase angle for red, and it's right here. That's red. And I can prove that by going, here's green, right? Wait a minute, you mean green is here, red's here, blue's here? I can make any color like this, with one exception.
But
There's
I see
0
something there on the
degrees.
Vectorscope that's interesting because your green's not
There's
in
an
the green
artifact.
box.
It's not. It missed. And who's out of calibration? I have no idea.
Well, the green looks pretty green on the shared screen.
Right. So let's
But
do blue.
that's the value of the Vectorscope too in these, because they came with that. If your Vectorscope was in cal, you had the Graticule that helped you adjust everything. But I remember helping AV guys at some large events back in the 90s too, doing camera operator. I did camera operator just for one day. It was really hard, but I got paid to do it. So.
Yeah.
But I had this panel of Vectorscopes and camera control units in front of me. This is back in the 90s, so.
Right. So in theory, I should be able to walk this around. So there's red. Oh, that's white. So there's red and green, green and blue, blue. So I just walked around the rainbow in the vector, and this is a phase encoded signal. That the phase is changing like this. It'll go red, blue, green, cyan, red, as it's encoding across the line. So now the way we synchronize, that color oscillator exists at both sites, at the transmitter site and at the reception site, and they have to be kept in sync, because if I'm going over here on the transmitter, if I'm going, hey, 21 degrees, on the receiver I go, yep, 21 degrees, it has to be 21, not 35 or something. Well, we have to have our oscillators exactly tuned, and that's where the color burst comes in. Let me see if I can amplify the color burst first. So there you are. It's 8 to 10 cycles. If I triggered differently, you'd see actual sine waves. So the trigger is making them look like overlaid sine waves. And so to answer your earlier question, what's the frequency of those artifacts from the pure colors? It's 3.58 megahertz. Right. And there's our color burst on the back porch, right here.
Exactly. As Alan was saying, it's a sine wave, but it's phase.
Phase encoded.
Phase encoded, yeah, phase modulated.
All right, so here's another function built into my thing. Let's go to RF. There's our color subcarrier. Okay, variable. So for testing purposes, remember when troubleshooting TV sets, we used to fix them, not throw them away. So you might have a stage that does something horrible to 2 megahertz. A component failed, a capacitor changed value or just failed, and you can't get 1 megahertz through, or you can't get your 3.5 megahertz through. So the test thing has the ability to send out different frequencies. So there's 1.5 megahertz in the composite video.
Yep.
2, 3. Now watch what happens when I
I
go
love
to
that.
4.2.
You're making propellers.
Yeah.
Hey, that's another episode we should do with Alan sometime. How to make fun Lesargis figures and other XYZ modulation fun in a oscilloscope.
Yeah, actually, I think there's. And unfortunately, I can't do, and I asked this of Alan, I can't do as much XY on my scope as I could in the old days, on the old analog scopes. I have one of those from the one of those Tektronix logo T-shirts. I don't have the actual module, but I have the.
We talked about that probably a year ago, didn't we? Yep. The old Tech logo was done as a signal generation.
It was an early meme.
It was. But that's fun too, because I looked into that when I was a teenager as well, because I was fiddling around with helium neon lasers, and I I never had the money to buy good mirror galvanometers, but I wanted to build my own laser projector with XY mirror galvanometers and learn how to drive them
Right.
with X and Y waveforms to draw images with the laser beam. And I'd seen someone do basic laser patterns, and I did this using little audio speakers with a mirror glued to a piece of metal that was affixed on one corner of the speaker, and the speaker
Right.
would vibrate the mirror. And I could do little like propeller patterns and stuff like that, or I don't know what you call it when you have a pen that swings around and draws those things. What do you call those things? I forgot.
Pink Floyd light shows.
Yeah.
All right. So I wanted to show just a couple more things. I'm actually running short this week instead of long like we've been doing the last couple ones.
Oh, there's still a lot to talk to and a lot of feedback, a lot of cool stuff coming in the chat too.
Right.
One thing, I'm on a computer that I haven't installed Discord on yet right now, so I'm not monitoring the Discord, but I think generally people just do the YouTube chat anyway. So
During the chat, yeah.
Yeah.
Again, we have a Discord channel, people. So thinking back to TV
Spirograph,
sets.
thanks, Chris.
Yeah.
You reminded me. It's a spirograph.
Oh, right. That was some cool math, wasn't it? For a kid going, oh, it's divisible by the number. Oh, it never is divisible by the,
A spirograph is actually the best way to introduce people to the Fourier series and the Fourier transform, in my opinion.
I never thought of it that way. That makes a lot of sense.
Yeah.
My sister had a spirograph man which used a swinging pendulum. So now you're combining physics with, the math of the gears and stuff. And I thought that was when it worked, it was cool. Magic eye pattern. What's the magic eye pattern? I'm trying to remember. Magic eye. That's so familiar. Somebody just mentioned in the chat magic eye.
Well, magic eyes I thought were also a display tube.
Oh, right. Cats. Well, I used to call cat's eyes. I actually have.
Yeah, and they could be used. That you can still find them in some boutique tube amps.
Yeah. Oh, I love the cat. Or you use them for multipath distortion. On your FM radio, you had a tube just for telling you which way to turn your dipole antenna. It was pretty cool. So the other things that are on my NTSC generator in the top here is sound, because this is meant to test
the whole
TV sets, the whole TV. Thank you. And so there's different tones I can inject. And then in a TV, there's an RF section, and we have not talked about the RF section. We've been talking about monitors, which means I've already taken what was transmitted over the air and knocked it down into, I think of it as a DC signal because it's only 0 to 6 megahertz, right? Compared to 54 megahertz where channel 2 starts and whatnot. Oh, by the way, I should have pulled it out beforehand. Hold on just a second.
Okay. I need to get some water too. My throat's still a little dry. Give me 1 sec.
Yeah, I don't have it handy. I was a licensed TV repairman at the age of, well, that's why I was going to look on the thing. I had to go take a test, and I had to know 54 megahertz was the start of the TV band. I used to have to know the start of the UHF band. All the things you probably need to like get ready for an FCC type test. So it used to be on TV sets. It's still there for RF TV sets. There's a tuner that takes the RF off air, combines it in a mixer with a local oscillator, and turns it into an intermediate frequency. So when you look in a TV set, they're amplifying the intermediate frequency. I can't remember the frequency, which is part of my test. But it's easier to amplify than 54 megahertz to amplify whatever I should look that up. The intermediate frequency. So we have an IF, which we call IF. The IF output is right here. And it's selectable. I can select channel 3, channel 4, or IF. You know what? I'm going to throw it on the scope and see what.
I really like your layout for the stream, by the way, today. It's great.
So my candy.
Yeah, just to be able to see everything laid out like that is super cool.
Oh yeah, and I lost the color bars when I unplugged that, and yeah, the knob's loose, so I'm probably not going to be able to. Yeah, I'm not getting the IF frequency. I should have checked that ahead of time. But so it's also got, and that's useful for alignment. In the old days, you look in the TV set, and there's all these cans in there. And you reach in there, hopefully not to get shocked. You reach in there with your your tweak tool, and you would adjust the IF cans, their coupling transformers, and you adjust the slug for maximum coupling of the signal. And so that's why these NTSC generators you couldn't do this without the right equipment. To align your TV set, you needed a signal generator. Well, that's what this is. And so you can do just the IF sections, or you can do the RF sections from here also. So that's what the little IF section on this thing is.
That's
cool.
So
10.7 kilohertz. Is that right? The 10.7 sounds right. 10.7 megahertz, maybe? 10.8? Yeah, somebody look that up.
Low, but
yeah, it's not kilohertz because we're embedding a 6 megahertz signal in it. Here's the tweak tool from my old days, 40-year-old tweak tool. And the trick was the cans are right underneath the picture tube, so you learn to bend these with your hand to make them right angle. And you can see I know how to do it, right? You reach in and you bend that down into the can, and then when you rotate it, it's rotating the can, but you're not brushing the high voltage with the back of your hand. So you learn to do a twist like this to tweak these things. So reaching in an old, dusty, dirty, smelly, greasy TV set was, it was just horrible back then. And sometimes you'd have to tie the chassis up with wires to lean it up like this. And then I've laid on my back looking up, it's like working on a car, to work on the bottom of the chassis. I mean, huge tube chassis, right?
Yeah.
They're not meant to be taken out while the TV's working. So how do you troubleshoot the bottom of the tube sockets while it's operating? You got to crank that chassis up into the air, and you can watch what you're doing. All tubes have high voltage on them.
Oh, yeah.
Yeah, 10.7 megahertz. Yeah.
40-year-old tweak tool was my nickname at school. That's hilarious.
Yeah. Right.
That's brilliant.
We had so many names for these dang things too.
Nose picker.
Some other color charts that I've used in my career. I've designed NTSC color cameras for theft prevention, where back using old CCD. This is 1990. I was using CCD image arrays, making my own NTSC camera, and I lived and died by this. I can't remember the name of this. There's a name for this type.
You do a white balance and then test on that, and then white balance.
You do a white balance, and then here's common used colors, and yeah, these were useful. I had big ones, and they were calibrated. We actually spent a few $100s for one of the targets I had, and it's a piece of paper, basically.
But it's highly specialized ink on the paper, right?
I don't know. I assume once you bought it, I assume there was no warranty on the paper, So, audio 45 for 46 megahertz video. Yeah, that sounds fair. So there should be 4.5 megahertz difference between the audio and the video IF frequencies, and that looks right. Yes. So, Alan, I'd say you're right, because the audio carrier is at 4.5 megahertz, so it comes out of the IF section, or it's in the IF section, comes out of the mixer 4.5 megahertz apart. So, yep. And if you have too much 4.5 megahertz, one of the things we used to run into was audio carrier artifacts. We had to make sure that the audio carrier, I want to say, was less than 10% once detected. But if you get these kind of herringbone patterns in your picture, it can be adjacent channel. To your left, if you look at the frequency spectrum, you could be hearing the 4.5 megahertz carrier of the audio carrier next to you. So there was a pattern. So as a TV repairman, I got to recognize all these interference patterns, because the TV is a wonderful piece of test equipment also. It's a visual. What do you get to work on that shows you the problem, you know?
Yeah,
so
it's all in the display.
Yeah, and I was known for walking in. So back then, remember, we had a horizontal control. We didn't have digitally controlled 15.75 kilohertz. It was this sloppy old oscillator, and you had to lock it on, and then same with the vertical. And then the tint control, a lot of TV sets, the tint would change as it warmed up. So everybody'd start they'd start normal color and turn green or something like that. So I was known for, as if I walked in your house, first thing I did is adjust your tint control on your TV. So that's it for me for NTSC generator. Any questions from anybody or anything they'd like to see further? Oh, hey, that's a great picture of. Let me expand this. And here is our vertical retrace time. So this is an example of the time it takes for the beam to get from the bottom of the set back to the top of the set. Each one of these is a horizontal line. I used to know it's like 23. I forget how many are in here. And there's things called serration where we actually move move where it's a rising edge or falling edge. And the earlier Commodore 64 got this wrong. Plain and simple, it was wrong. And when we got to the digital TVs, guess what? The vertical rolled. We had the wrong number of pixels total in the whole thing. And we had to do a rev of the VIC chip. Once the vertical hold went away on TV sets, we had to rev the VIC chip for that. And so that was during my time. So, but here's our vertical, here we go. Here's our vertical retrace time, and then here's the top blank lines, right? You can't see them. They're up here on the, above the white, yellow, blue stuff. These are the blank lines, and so then around line 20.
They're off the top edge of your picture tube, yeah.
Now, when I was doing let me make this smaller again. So, as I said, I did a whole video system in the 90s for theft prevention, where I had 24 cameras all talking to a microprocessor, and it didn't need to be NTSC other than the NTSC ratios, but the timings were kind of variable. It could be variable and whatnot. And what was my point in that? We had one of the video sources, we could only get 4 out of 5 frames a second out of it. And the customer initially, so it would go frame, frame, frame. This is like a security camera where you get 5 frames a second. Mm-hmm. This was an adjunctive channel. This wasn't the main channels, but it was just there for management of something. And the customer said, yeah, it can like go have a pause in it. So you'd see something move and then pause and then move and then pause, because I was only processing 4 of the 5 frames. Then, of course, they changed their mind and said, that looks horrible. And I said, well, I agreed, but you agreed to it. I was able to take 4 frames and spread it out over 5 of NTSC by creating a digital phase lock loop where I got into line 17 here, and I made line 17 be a variable length. So I'm modifying the NTSC standard to my own warped conceptions, but I tried to do it in analog, and I couldn't do it, but I could sit there and make the NTSC signal be a variable length. So over the course of 1 second, all the timing lined up, but I had actually taken 4 frames and stretched them out to make them 5 frames. So the weird stuff I did in the 90s, you know? So, all right, let's see what else we got. TV modulator, what fault caused to bleed sideways in long lines. I have an old RCA, bleed sideways. If there's a smear you get, like a red smear that goes to the right. And I want to say I used to see that when it was out of alignment. But I can't speak more about those. Other artifacts you'd get if you had, remember we're painting a picture, right? Using the yoke of and look at the old video that we did last week. If you lost the scan or unplugged the yoke, you actually got a dot. If you had high voltage, you'd still get a dot in the center of the screen. And we used to call that, you turn off your TV set, you'd get that dot, and it was called a sniglet in the old days.
And it
so it's just one of those. Yeah, it does. You end up with the dark spot in your set. But it also told me, you know, if the picture grew and got bigger and smaller as the image changed, it would tell me there's poor high voltage regulation. If the picture, when there's a lot of white and a lot of higher voltage, the picture would bloom a little bit or decrease, and the amount of high voltage regulation would control where that picture stayed the same size or not. So that was one of the things.
But I wonder, like, if there's if Electron Ash is having this issue with a module. Oh, it was Mr. Guru. Sorry, Mr. Guru has this issue with a modulator that's taking the video and modulating to RF to go into the antenna input of a set, right?
Oh yeah, he did say modulator, didn't he? I missed
bleeding,
that. Yeah,
it's bleeding sideways.
I don't know what that
I feel
be.
like it's probably has a.
Because it's in the RF domain. Yeah.
I'd say
I don't know what would cause an artifact of a composite video once detected. I don't know of an artifact in an RF modulator that could cause a composite video artifact, if that makes sense. Because it's modulated by that point. You're either going to mess with the carrier, but you're not messing with the composite video till you detect it.
Yeah.
And by detecting, I mean we run it through a diode, basically.
I'm wondering if the carrier is not stable, like
then you'd get color artifacting. You'd get, that. I don't know that, because the modulator doesn't know what to the right means. Composite video does. It means everything behind me, right? And it does in the modulator. But I just have a hard time. I didn't see many things in the modulator affect video other than signal strength. Or the modulator or the tuner, I should say, too. The tuner is all about signal strength. You get it tuned in. Once it's in and you lock your 3.58 megahertz chroma, there wasn't a lot in the tuner that could cause artifacts that I remember.
Electron Ash is saying could be bad caps on the neck board and...
Yeah, and that's almost always true these days when we're talking about 40-year-old stuff, so...
Yeah.
Well, that's it for me. I'm talked out on my 40-year-old NTSC generator. I wonder what year that thing was made, my 1251. I do have a second one, because at one time I thought my B&K was broken. And here's a Tektronix, whatever it says there. I don't have my glasses on.
TSG100 or something?
Yeah.
Signal generator.
And it does have quite as many things, but this is very useful, too, for doing that. It doesn't have the audio and it doesn't have the IF. But it's a good signal generator for doing your signal chain.
Cool.
So, yeah. So that's a Vectorscope. Oh, yeah. I moved the picture. That's a Vectorscope, an NTSC generator, and we also dialed in on a spectrum analyzer. We took a look at the color burst, and we played with some color bars and talked about purity.
That's a pretty thorough look into never twice the same color.
Right. And so PAL was invented because if you did kind of, there I go. See, I'm adjusting the hue again. Remember, I think of hue as the Vectorscope. If noise forced me red, for example, what they did is they inverted it, so now red is this direction, the next line. So it's phase alternating line. So they would do that. You notice I'm using the hand with all the fingers.
Yep.
But that was meant to reduce the chroma noise by having it average out. So a phase alternating line on an oscilloscope, you see it and you go, oh, that makes so much sense. It just, you go to line 17 and the color burst starts by going high. You go to line 18 and the color burst starts by going low, you know, and you can just picture it.
Yep.
So, it's Alan saying he sold his NTSC. It's a miracle I still have mine. I almost gave it to Wes last time he was here, but I thought it was broken. So, and what would he do with it, right?
I like so many people now would never have a use for one because I don't own any old TVs or if I had some classic Commodore monitors like some of our viewers do, I would absolutely need this gear, but.
Right. Oh, this used to be vital. This was my pride and joy at one time was my NTSC equipment and my scope that I could see the color burst with. You know, if I could dial in on the color burst, especially on line 25 or something, I was in hog heaven on the odd field. Then I was like, "Ooh," you know, and because we're probably seeing odd and even fields, that's probably why why you're seeing both of these superimposed. I didn't try and play with the triggering to get that to be just the one field or the other. But now you got me curious. Trigger menu.
Well, but that's why we can see. That's why we can see in the scope with persistence. You see both phases there.
Right.
Right. It's cool that you can trigger on even and odd phases too, or fields, I should say.
Right. No, it's still doing the same artifact,
okay.
So I'm actually at a loss to explain why that's showing them not just a clean sine wave. So maybe that's a question for Alan at some point. Do a single shot on the scope. Yeah, that would work. There you go.
Yeah, there's the thing about CRTs and some of the analog tech like that, particularly for video. Yeah, so we can see just one phase there now.
Right.
And so, like Electron Ash was saying how good the CRTs look in retro game consoles, and from the pictures posted on the Discord, what we're talking about here is when you mount a monitor, a CRT monitor, and you turn it to portrait mode, for example, and you put it inside a nice wooden cabinet and you have 1942, 1943 in there. There is something special about that. They look incredible, even though they're low resolution. Low resolution graphics in the 80s still looked really good because as long as you had color, you could draw really nice sprites, and as long as you had, like, you could have smooth animation, and it was fine. The moment you put that sort of Commodore 64 style graphics with what is it, 272 lines or 200 lines on a 15-inch or even a 13-inch TFT panel, you no longer get the analog
averaging and
bleeding things across. You get hard pixels. And so there's a natural anti-aliasing that you get with CRTs that actually makes everything look really soft and nice. And we don't have that anymore.
Right. Yeah, I used to say it was resolution and imagination. We thought it looked great back in the old 2600 days. It's like, yeah, that looks like a tank. It's a tank. Look, it's a tank.
Yeah.
Because nowadays you have to play World of Tanks if you want to see a tank.
Yeah. Yeah, and we actually now demand graphics cards that cost more than all your motherboard, CPU, and memory combined. It's like, what the heck is with that?
Right. So, any final questions from the chat? We'll talk here same with vector monitors. I'm not sure with local dimming, HDR. My name is no board faults.
Yeah, OLEDs.
So
that's the thing. If you have a good 4K monitor, it's a beautiful image, but you must have content that matches that, and that's hard. That's still. I've been frankly disappointed with 4K TV at home on the wall, how much most of the content still just doesn't look that good.
So one thing with TV sets that you get these days, you have to go in and turn off. They have this adapted motion filter, and I you know what? I should find a link for that. But the TVs ship with something that they think looks better for people that don't have a discerning eye. And you actually have to go in and shut that off if you want to see the actual signal the way it was transmitted.
I
can't remember the name for that.
On my cheap Costco TCL Roku TV, it's probably
bet you can
turn off.
Now, I bet it's under advanced color management.
Okay.
And they
so
call
what's
it,
it called
there's
again?
an adapted, it's like an adaptive motion filter or something like that. They're
Okay.
basically trying to average 2 frames together to get you a blurry frame in the middle and
I
stuff.
hate that. I don't want that.
Right. I want to
I
see
don't
the
want
2
that.
frames. Right.
If I'm dealing with a high resolution LCD or TFT of some kind, I want native, everything pure native. It's
Right.
going to be different if I'm doing retro gaming. I'm going to use a lower resolution screen and make it really small, and just
Right.
have a handheld thing, because it's
Here you go. I can't believe I got it to come up. I Googled adaptive motion filter Tom Cruise, because I know he went off on a bend about this because he's making movies and then people say your movies look like crap. And if you Google Tom Cruise adaptive motion filter TV, it says Tom Cruise explains how to turn off motion smoothing on HD TVs. So it's motion smoothing is what they're,
Motion
and it's an
smoothing.
averaging.
Yeah, I
they're
don't want
trying to
that.
create an intermediate value in there. So, yeah, it's turned off on all my sets, all my cheap LG sets and the expensive ones. They all shipped with it turned on, and they all had the ability to turn them off. So,
Yeah,
good.
well, I'm going to be looking for that as soon as I get home.
Yeah. So, or Google for it at least and see, where it is on your set is my recommendation. All right,
Yeah.
I'm done talking. I'm going to go play with my chickens and ducks now or something at least.
Yeah, well, we're past the hour, so we could stop now. I had other stuff I could have talked about, but since we're past the hour, we might as well just save some of that.
Yeah,
for
let's do
next
that
week.
and save it for next week, because Ben's bench behind him before every show he shows me his new stuff, and we could do that probably at the beginning of every show. Is just show your AC meter. Is that still sitting next to you?
We'll talk about this next week, because
We'll talk about it. But here's the eye candy for next week.
But I got one of these from UCSD surplus sales. I haven't tested it. I don't know if it works yet, but these are beautiful instruments. This is an AC voltmeter.
Here, I'm going to try and make you big here.
Right.
Right.
HP
Love 'em.
400E. It's got a beautiful classic meter and meter bridge circuit to drive it, so it's true RMS. But what's valuable about these over a regular multimeter is it's true RMS in volts and in dB from 0.001 or minus 60 dBV all the way up to 300 volts over 10 hertz to 100 megahertz.
Okay.
So this goes way up.
It's
into
an RF
RF
meter too. Yeah.
It goes way up into RF and gives me dBV and RMS voltage, and it's true RMS the whole way. It's got I can optionally battery power it from plus or minus 35 to 55, so I can isolate it. That's extremely useful and necessary sometimes. Got my AC output and a DC output from the meter bridge. So I can measure a DC output from that's exactly proportional to where the needle is.
Right. And I love the mirror on there for anti-parallax. That little mirror strip is just a sign of the days.
Yeah.
So
So
Alan said his paint is peeling up on his scale, and he must have the same one, and it's interfering with his needle movement. So it's old stuff's a bitch.
The scale's in pretty good shape, but the plastic coated, I think it's vinyl, the vinyl coating or PVC coating on the side panels and everything is a little bit gummy. It's got a slight
it's
sticky
degrading.
film on
Yeah.
it. So I'm gonna I'll probably take the whole thing apart and
It's devulcanizing.
get the stickers off, and I'll wipe the panels down, hopefully with something that doesn't eat it worse, but gets the goo off.
I wiped something with isopropyl alcohol last year and ruined it. So be careful.
Yeah.
I thought IPA is. I thought that's safe, and no, I ruined something. It's forever gummy now. So
I'll have to research what to use before I do it. Yeah. So I don't want to.
So,
but we'll look at that
all right.
next week.
Excellent.
And some other things. I'll have more. You can see behind me. It's almost set up there. I've still got some crap on the floor I've got to sort out, but
yeah, crap being an official term.
Yeah, I also got a used Frey Scientific power supply, another power supply, adjustable 0 to 20 or 0 to 30 volts up to 2.5 amps. I plugged it in and it started crackling. So we'll take that apart and see what we see inside. That'll be fun.
Yeah, take pictures. So
yeah.
All right. Hey, Ben, my friend, it was excellent talking with you. Everybody, thank you for sticking around. We had a fun show here showing my old NTSC generator. What was that? Never the same color twice or whatever.
Never twice the same color.
That's it.
Or never the same color. Yeah.
Yeah. All right. We will see everybody here next week. Take care.
Good to see you, Bill. Thanks, everyone, for joining us. Join the